Welcome ENET 130 at Bellingham Technical College. This is our half-quarter study in semiconductors, continuing our series on field effect transistors. This is our second lecture dealing with field effect transistors. We started with the basic principle of a field effect transistor, how it differed from a bipolar junction. And we started with what's known as JFETs, or junction field effect transistors. We're going to build on everything we did with JFETs and introduce another variety of field effect transistors known as MOSFETs, metal oxide semiconductors, field effect transistors, otherwise known as insulated gate. And that second term will make a lot more sense when you see a picture of it. So we're going to skip right to a schematic and use that to describe how these work. MOSFETs, or insulated gate field effect transistors, come in two flavors, actually four. We can have N-channel or P-channel, just like we did with JFETs, and we can have what's known as depletion mode or enhancement mode. So N-channel, P-channel works exactly the way JFETs did. It basically is whether or not we have an N-doped material, which will form the main current carrying channel between source and drain. So this schematic here in figure 12.1 is an N-channel. So we are going to apply a bias to the gate that will control the current that flows from the source to the drain. This is the controlled signal. And we're going to put in a voltage signal to the gate. Which will delta V, which will control this flow. Very much the same as we did with the JFET. The difference that we can see in this case, though, is we don't have underneath our metallized terminal of the gate, we don't have a piece of P-type semiconducting material the way we did in a JFET. What we have that's represented by this dark kind of grayish layer of material is a metal oxide insulator, hence the name metal oxide semiconductor. That's a metal oxide like silicon oxide glass. It's a true insulator, not a semiconductor. It's a big band gap, so no current's going to get through. What will happen, though, is that insulating layer is going to form basically the dielectric of a capacitor. So what we'll do is we'll apply a voltage, which I probably shouldn't have just erased there because we're going to need to apply a voltage. And just like in any capacitor, we're going to apply a voltage across two conductive layers with a dielectric or an insulator between them, and we're going to get charge on both of those layers. And the charge on the bottom layer going down into the N channel is going to form another depletion zone that will control our current from source to drain, just like the JFET did. So we're going to apply a voltage. We'll just draw it with a little terminal. And we're going to apply a negative voltage to the gate. Well, if we have a capacitor, say, here's two parallel plates to a capacitor, and here's my dielectric material in between that I'm kind of drawing in with a squiggly line, and I charge one side up positive, the other side will be negative, and there'll be a voltage drop across it that is equal to the total charge divided by my capacitance. Well, in a MOSFET, the metal layer of the gate and the fairly conductive and negative charge carrier rich channel below it, or a positive charge carrier channel in the case of a P, those form basically the conductive plates of what's a capacitor at the gate. Okay, so here's one plate, and here's effectively the other plate, the N channel itself, with the metal oxide layer forming the dielectric. So if I bias the gate with a voltage that basically puts a bunch of negative charge up here at the gate, because I maybe hooked it up to the negative terminal of a battery, the bottom big, I'm going to have to get effectively a positive charge down here. Okay, well, if I have a positive charge in an N-type, N-doped semiconducting material, what that means is I've annihilated a bunch of electron charge carriers, and I've created a depletion zone. I've effectively, you can think of it as I've combined or driven the charge carriers away. So I've driven the electrons away from this area adjacent to my oxide layer. So now current has to flow through a more restricted channel. This is similar in a way to a JFET in that we grow a depletion zone by applying a bias to the gate, but instead of having the double effect of an oppositely doped semiconductor layer at the gate, we literally just have the capacitive effect of our metal oxide and the metallized lead. So it achieves a similar type of throttling control over source to drain current, but it does it in a little bit different way. So you think of a metal oxide or insulated gate field effect transistor as literally just being a capacitor on the top. Okay. So we can show that a little bit better with the biasing hooked up. Now we'll show it in a good circuit. So we have a common across the bottom, and the source is attached to the common. So we've got positive current or positive voltage applied to the drain. So electrons will flow, and this is a dotted line showing electron flow. Electrons are going to flow towards the positive, so there's our source to drain voltage effectively being achieved here. And we've got the gate hooked up to the negative terminal of our source to gate voltage, bias voltage, and here's our capacitor effectively. Negative charge at the gate, positive charge down in the channel, grows the depletion zone. Okay, so just like a JFET, a major characteristic of our depletion zone insulated gate or MOSFET is it is default on. If we don't apply a bias voltage to the gate and grow that depletion zone, we have tons of conductivity. In fact, it is possible to, and let me go back here, we can actually apply, if we wanted, we could apply a positive charge to the gate, and we would actually widen out a little bit. We could effectively make a bit of an effective widening of our N channel, which was something we couldn't do so much in the field effect, or excuse me, in the junction field effect in the JFETs. So a depletion mode MOSFET can actually work by throttling your current, by applying that opposite charge to the gate in depletion mode, or you can actually widen the channel a bit, and that's known as enhancement mode. So here's a normalized curve showing a normalized gate to source voltage and then normalized drain current. So if we apply an increasingly negative charge to that gate on that N channel material, our drain current goes down because we're throttling it, just like in a JFET. But if we go the other way, we can actually widen the channel a bit and increase the current. So that gives us a little more room for circuit design. We can actually throttle in both directions. We can open and close that channel a little bit. Okay, mathematics to relationships between the drain current and the gate to source voltage and maximum drain current in that steady state. This is exactly the same as a field effect. As a junction field effect. These are all a field effect. It's similar to a JFET. So our source to drain current versus applied gate voltage expression is exactly the same. It's that same parabolic expression, and the same with the transconductance. The slope of this will be the same. One word of caution, and you'll see this in the red highlights everywhere. And I'll go back to our sketch. There is no way to flow current from the gate into the device. This is an insulator. Because we can't flow current, we can't discharge accumulated charge. So the fact that we have no way to effectively ground that gate terminal, because it's sitting up on an insulator, it makes these types of devices extremely sensitive to electrostatic discharge voltage spikes. And in fact, you can ruin a device just by taking it out of its plastic container if that plastic doesn't have a charge draining polar component to it, the pink plastic. So electrostatic discharge sensitive devices you may have heard of, this is it. And it's this insulating layer that makes it electrostatically sensitive. So that is a very, very important practical word of caution when dealing with these components. If you are building them in your circuit, always try to make sure you don't allow charge to build up. Generally speaking, that's going to involve using what's known as electrostatic discharge type of grounding and clothing. You obviously don't want to necessarily ground yourself when working with electronics, depending on how you're doing your safety. Generally, you want your circuit grounded and you not. You certainly don't want a voltage source finding an easy current path to ground through you, but you can allow enough conductivity through your fingers to bleed off that very small amount of electrostatic charge. So there is a whole protocol of static discharge sensitive operations that are necessary to work safely with these devices. Totally beyond the scope of this class how to do it, but know that is there and know that special handling is required, and that is the reason. Okay, insulated gate, static sensitive. Okay, so we can go one step further, and these are just summaries very similar to JFET. So here's our transconductance expressions. So our G sub M0 again is the slope of our drain current versus source drain applied voltage when we are not closing or opening. So it's for effectively the slope when we have not applied any source drain voltage. And then here's our slope at any applied source drain voltage here. And remember, in the transconductance, for a MOSFET that can work, it's a depletion MOSFET, but it can work in enhancement mode. This expression could change sign. We could have a VGS that is positive or negative. So we could have an expression here that becomes greater than 1 effectively. So that would change. Otherwise, everything exactly the same as a JFET, but we can work in enhancement mode. Know that we are achieving our signal throttling. Our gate to source voltage, applied voltage, is basically charging a capacitor. We have electrostatic sensitivity. We're default on just like a JFET. We have a little bit different symbols here for our depletion or D MOSFETs. So same kind of convention regarding N channel, P channel in the direction of the arrow. Okay, so that is it for D MOSFETs. Very similar to JFETs, but mainly that insulated gate, different mechanism of creating our depletion zone to throttle. Okay, so here's where we get to something that is really kind of fundamentally different. This is another flavor of MOSFETs, and this is known as the enhancement mode. So we talked about how a depletion mode MOSFET can work in enhancement mode. We can actually widen that channel a bit by reversing the polarity on our gate capacitor effectively. We can design a device that is default off and requires some action at the gate to create a channel at all. Okay? So this is a schematic of what's known as an enhancement MOSFET, and this is also an N channel, except it hasn't grown its channel yet. So we have a source voltage input and a blob of N material that is embedded in a P material substrate, and the same over here with a drain. So right now, with no gate bias applied, bias voltage gate to source, we have what is kind of like a bipolar junction. So we have a PN junction here and a PN junction here. They're opposite orientation. We can't get any current to flow. This current can't flow. No current. Because if we forward bias this junction, we reverse bias that. So that's basically back to the dilemma of how does a BJT work. This is not a BJT. So we're not going to run current through the gate, certainly, because it's an insulator. We can't do that at all. We'd ruin our device. So we're going to do something totally different. In this case, we're going to use the fact that we can charge our capacitor and create effectively an area of opposite charge on the other side of our metal oxide insulator. So we're gonna hook this gate up to the positive side of a biasing battery. And in so doing, we're going to charge the gate positive, and we're going to create an effective negatively charged region. Okay? And in fact, we're going to make this region so negative, it's going to have electron majority charge carriers. And it's going to form an N channel. We're going to grow an N channel electrostatically by applying positive here, and we're going to rearrange the charge carriers via the electric field that we throw across that dielectric. Hence the term field effect. We got an electric field in this capacitor that's basically the gate with its insulating dielectric layer. So we're going to use that field to grow us a channel. And here's a schematic of basically how this works. And our book calls this the N-type inversion layer. So it's also known as the enhancement channel. So very similar to growing a depletion zone, except we reverse the polarity and we apply quite a bit more. And instead of just having an intrinsic semiconducting layer here, we actually have enough N-type charge carriers, electrons, to now have a channel. So opposite what we had before, the more charge we apply to the gate, the higher which we achieve by having a higher source to gate voltage, the bigger the channel. So now we're forming a pathway. So we're going to get a bigger path the more charge we apply here. Okay, if we want a mathematical expression again for that constant current drain current portion of our gate to source versus drain expression, like we had on our depletion MOSFETs and JFETs, this is the analogous expression for an enhancement mode. So here's our in this case we don't have a gate to source voltage where we would cut off current, but we do have a gate to source voltage necessary to start. So we have to apply a certain amount here to get that channel growing and start conducting at all. So that's known as the V gate source TH, or threshold. So that's what we'd start with. So when we apply V gate source equal to V gate source threshold, ID is 0, we've just started. But if we apply more, if V gate source is greater than V gate source threshold, then this term is greater than 1, we square it, and we still have that squared relationship, and we can get some current flowing. So instead of a 1 minus with a fraction, we now have source drain current, our controlled current, the big signal we're controlling, is now directly proportional to the square of the gate source voltage that we apply in excess of our threshold. So we're opening that channel, we're building that enhancement channel with a small voltage signal, very small voltage signal, because remember, we're just charging a capacitor. And in so doing, we're going to have the squared term of that control the drain current. Okay. And we can get the slope of this expression, the transconductance, by just taking the first derivative, and it's a very simple expression. Rather than having a squared, we just are linearly related now. And now we don't have a depletion mode at all, we only have enhancement mode, so this would be our just a plot of that parabola showing how we can get higher drain current with increased gate to source voltage. Okay, last quick topic. We can construct various styles of an enhancement mode MOSFET, and some for better signal, some for faster switching, more sensitivity. This particular one is designed to carry a lot of current. This is known as a power trench enhancement mode MOSFET. So same kind of idea. We're effectively going to need to grow some N-type material through here to allow us to conduct. But what we've done is we've made it really easy to grow a channel, and we've increased our interfacial area. So the more interface you have and the wider the path for current, the better you are. And rather than having us go across like so, like we did, we're just going straight down. The drain is now connected to the bottom. Let me erase a little bit to make that clear, because I've cluttered it. The drain is the entire bottom of the device. So we've doubled the area of source. We've made the enhancement path we have to build very small. All we have to do is bridge that, and very likely we have a lot of heavy doping down here, so our ohmic losses are small. So we can build our enhancement channel with our gate, with our capacitor. We'll apply a positive signal here. And we'll end up making our negative enhancement zone right here, and then current flows straight across. So the P material will grow an N channel through it, but it doesn't have to grow very much, and we can conduct a lot of current. So this is a good example of how the design of the device that's fabricated in the semiconductor device fabrication facility that we just buy as a pre-made device in a package with leads. The design of that device is specific to purpose, and the effects, the benefits of that design are embodied within the spec sheet. So I would expect a device like this to have a much higher maximum current, but probably be a little bit less sensitive, and maybe have differences in threshold voltages as well to turn on and off. So that is it for our very brief coverage of MOSFETs as a second type of field effect transistor. I will return back. There was a note that I want to share with you regarding, because Mr. Fiore does not include a sketch. Enhancement mode MOSFETs have a different symbol for a circuit schematic symbol. They look similar to a depletion mode, but the source drain vertical line is dashed, indicating that it has a default off status. And if you look at the tutorial websites on electronic tutorials, they'll have pictures of that that type of dashed as an indication that you have an enhancement mode. So there is a different circuit symbol for an eMOSFET versus a DMOSFET. And look for the dashed line in the eMOSFET to indicate default off. No gate source voltage, no conductive channel, default off. Okay, very last point. So we are now done with our discussions of field effect transistors. In terms of topic coverage, we won't be doing an extensive application of these in circuits the way we have with bipolar junctions, but they do have an analogous role in that a small voltage signal will control a larger current signal. We will see these again in later classes. Digital, some of those devices, digital logic gates, work very well with field effect transistors for current control.